Hello everyone, welcome to the class ECE 451. Now I'm recording the lecture of the Wednesday's class. This is also the last class with new material. Alright, we are keeping working on the discrete time system with the state space equations. Alright. Need to turn around. Yeah, now it's good. Okay, so we consider system in state space. It is x of n plus 1 equal to a x of n. Okay, let me use k for here. N we can use for the dimension of x. It's k plus 1. That's k plus b u k, u of k, and y of k are equal to cx of k plus d u of k. Okay, we consider this. This is discrete time system. Discrete time system in state space. Then we want to consider several things. Actually, two things. One is the feedback, one is the observer. So first one for the feedback. First day feedback. First day feedback. I give a structure looks like this. We have x of k plus 1. Now here I have a delay. In the z domain, delay is just the z to negative 1 or 1 over z. Then this side will be x of k. Okay, x of k times a and u times b You see, this is almost as same as the continuous times case. And also here xk times c and u times d. I have c and d. Put them together. Then we have y of k. Right, the system looks like this. Okay, for the feedback, similar, we start from here. With this one, go backward, and times k here. I need a, okay, summation. This is r of k. This is a positive, this is negative. So I replace u by r minus k x. So this is the full state feedback. This is full state feedback. By this feedback, now this is structure, right? In equation way, we rather than these two, we need a third one. We need a u of k equal to r of k minus capital K times x of k. So this is like 1, 2, and 3. We have these three equations together. Then we have a full state feedback. Okay, now we try to consider the pole of this system. Yeah, similar thing. We need to consider the pole. How to do that? We combine these three together. Just plug 3 in 1 and 2. Plug 3 into 1 and 2. Then we have x of k plus 1 plus equal to a times x of k and b, you say bu, okay? Bu, so b times u. B times u, we have another x of k, so it's minus k and the b in front, bk x of k. Alright, and I still need this. This is b times r of k. And y of k equal to c xk and du. In du we still have xk, so I put two xk together. So this will be c d times this, right? Minus negative. Here's a minus, so it's a minus d times k and x of k, and plus d times r. So we have these. Okay, then the stability, like stability, or you want to choose k so that the after the feedback, the system, after added the feedback to the system, we want the system has certain kind of poles or some features. Then you can just choose the poles based on this, right? Based on this, so we can choose poles by select different k. Right? You choose different k, then you can choose your poles, right? And these poles, the poles were certified the equation determinant of now is z in another S domain. After the transfer function z transform, we go to z domain. So this zi minus a plus bk equal to 0. The poles will satisfy this. If you know who are the poles, you select some poles. Then you know the root of this one, and you need to select a k. You know how to do it, right? This is what we did for continuous times case. So k were equal to we say the functions occur in the place of a, b, and the pole list. Okay. The poles, you say the pole list equal to pole 1, pole 2 to pole n. Suppose we have the size n, order n. Yeah, this is pole list. So k is just this one. And we also know this, we have a formula. This is 0, 0, 0, 1. Then is C inverse times we say is alpha of A, where alpha of A equal to A minus P1I times A minus P2I until A minus Pni. Okay. So you can calculate it directly from here, or just use the function place. It's the same with the continuous case. Okay. The only thing different here is not integral. Here is a delay. This is time delay. Right? Delay by one step. In z domain is 1 over z. And here is not derivative. Here is a x of k plus 1. So this is like a next x. Right? This is xk. This is xk plus 1. Okay, so this is the full state feedback. Second thing is the observer or estimator. Similar. It's still similar with the continuous case. I give the graph. Okay, I put it here. I need a 1 over z here. Then I have x of n plus 1, and outside part there will be x of n. And then go back. We have a feedback a times x of n do summation together with b times u. Here I need to come up. Okay, ut here, un, uk. Oh, sorry, I put n again. Yeah, sometimes confused. K, lowercase k, uk. Okay, this is u of k. U of k here, and it's coming up. Here we have a C, here we have a D, then combine them, we have a Y. Right. Okay, then the estimator will be things same with these. The only thing is we have another x, so here's a 1 over z x bar of k plus 1. Here's a c, here's a x k, x bar k, and the feedback a. Okay, and here's a b. Okay, this will be u, so u just coming from here, right? Same u. You can also use this b times u go to here, then you just use 1b. But you already suppose this part is non-available. You cannot see what happened inside, right? So you need another b here. And then here you are. I have another. I put d here. D here. C and the D go together. C times x bar, D times B. Then here we have y bar of k. And we will compare the difference between these two. Here's a positive, here's a negative. Then we have this is a y minus y bar, and go to L. L, and go to here. Go to here. Alright. Okay. So then by this way, okay, this part is a plant, and this part is a observer, estimator, observer. Right. And what we will do is we will select L so that y bar a limit, say like this, t go to infinite, y bar equal to y, or we say y minus y bar is 0, or limit t go to infinite, positive infinite, x minus x bar equal to 0. So we want these two, right? Okay, then what we will do is, we still need the equations. So here's the structure. The structure is make more sense, right? It's visible. You can see it, so you can give the structure. Now we give the equation. We just base on the structure. We can have the equation very easy. The original equations, the plant, we have the equation x of k plus 1 times, not times, equal to a times x of k plus b times u, right? B times u. Yeah, this is xk plus 1. And then y of k equal to c of xk cx of k and d times u of k. Right, this is the plan. And then the observer, we have x bar of k plus 1 equal to a x bar of k plus b u of k. Right. X bar of k plus 1 equal to a times x bar and b times u, and we have one more, plus L times y of k minus y bar of k. This is the x bar. And then y bar of k, we just copy this formula, but now is a cx bar of k and du of k. Okay, so now the whole equation looks like this. I gave the these are the estimator. I say this is 1, this is 2 equations, this is 3, this is 4. 4 equations, right? 4 equations. Now I subtract them. So 1 minus 3, 2 minus 4. 1 minus 3, this one minus this one. I have x of k plus 1 minus x bar of k plus 1 equal to this one minus this one is a times x of k minus x bar of k, and then bu minus bu, they cancel, and only left, notice left is this one, so 0. Here's no y terms, but here we have, so 0 minus L times y of k minus y bar of k. Alright, yeah, and then 3, not 3, this is 3, so 2 minus 4, 2 minus 4, right? 2 minus 4, we have y minus y bar, yk minus y of k minus y bar of k, okay, this one minus this one, and equal to c of x k minus x bar of k, okay, this one minus this one, then d minus du minus du, they cancel, so we only have this. So this is a 1, 2, 3, 4. This is a 5th equation. This is a 6th equation. Okay, plug 6 into 5. Right. Replace this y by this one. Then we have x of k plus 1 minus x bar of k, and this side we have xk minus x bar k, and here's another xk minus x bar k. So both are some matrix times xk minus x bar k. I put the matrix in front. The first one in the matrix is A, and the second is negative L times C, right? Negative L times C. Then here's a x of k minus x bar of k. Alright, so the other thing we need to do is, I got something wrong? Oh yeah, here's a plus 1, sorry. Hey, this one minus this one. Hey, this one minus this one. So this one, so here's good, okay. Yeah, here's a plus 1. Yeah. Okay, so based on this, if we want x minus x bar tend to be 0 for large k, let me see. Did I put the wrong thing? Oh, I put the t. It should be n. That should be k times k. I'm sorry. Yeah, we want this one tend to be 0. And actually, if x, the limit of x minus x bar go to 0, then the limit of y minus y bar is also 0, right? Because y is L times this difference between y is c times difference between x. So x tend to be 0. This term tend to be 0. Then this one also tend to be 0. So the thing is we need to select the poles based on this one. Make the x minus x bar tend to be 0. Okay, so if the pole is determined by this, determinant of A minus LC has only roots, okay, equal to 0. If this one equal to 0 has only roots inside the unit circle. Then the limit of k go to infinite, x of k plus 1 minus x bar of k plus 1, doesn't matter, plus 1 or no plus 1, and this one equal to 0. Alright. Okay, then so we can have error by R equal to, this is a place of A transpose, C transpose, and the P list, where P list equal to P1, P2 to Pn, and every Pi, the absolute value is smaller than 1. That's it. You know. So you select, it's your choice. You select some Pi. Each Pi is absolute value, the magnitude is smaller than 1. Then you have a list of poles and put it here. Then here you have the original system is A, B, C, D, so you have A and C, right? You put A prime, C prime here, and the pole list here. You can get there. So this is quite similar with the continuous case. The difference is you need to choose poles inside the unit circle. Inside the unit circle, not in the left half plane. It is inside the unit circle. Inside the unit circle. And similar, we also have the condition for the controllable and observable. So condition of controllable. That means we can find the k for any list of poles. You know, any pole, any poles. You can put the pole to anywhere. So because this is a controllable. The condition is just C full rank. You can write as a rank of C equal to n, or C inverse exists, or determinant of C do not equal to 0. Yeah, same thing. Yeah, same thing. Alright. So this is the condition for controllable. And the similar condition of observable. So we can find L for poles inside the unit circle. Yeah, this time you need a pole inside the unit circle. You know, then you can make X bar will close to X, or Y bar will close to Y. The limit is Y. This condition is that O has full rank. Similar, that means the rank of O equal to n, or O inverse exists, or determinant of this O is not 0. Right. Now, of course, you should know what is C. C will be B, A, B, until A to m minus 1 times B. And O will be C, C, A, until C times A m minus 1. Yeah. What else? Yeah, therefore for the feedback and the observer in the discrete time case, it's just like this. And then you can consider some change, like you want to combine them, like you want the feedback based on the observer. Now I have feedback, right? Feedback. And you can use this X bar to give a full feedback, right? You give a full feedback. You times K here and go to here, right? Yeah, if you're interested, you can do by yourself. You can also read the textbook. I have that textbook in the blackboard. Yeah, you can see it. And there's let me see, anything interested. Yeah, one thing interested. So we can have another kind of problem. Here is what is a controller? You know, we have a system here, right? You have a U as an input, and after you give the feedback, you have R is an input. And if we can consider things like this, we can select a different input to make the output satisfy certain requirement. For example, you find the input so that Y start from its initial value. For example, initial value is 5, and your goal is make this Y of K reach 100 for a certain requirement, certain reason you want Y reach 100. Then can you find the R so that the Y start from that initial value 1 and finally reach your requirement 100. So in that kind of problem, you are not find something here. You want to find R. You want to find suitable R. Now, of course, you also determine on K, right? So after you determine the K, so suppose like you have plant, the plant maybe is not stable, and after that, after select K, you make the whole closed loop system to be stable, and then you want to select the controller U of K. You select the U of K. You can find the U of K by input this U of K. The system, or like you can drive this Y to reach certain value, like you want 100, then the certain after Y will really reach 100. Things like that. Yeah. That kind of problem is we also call it as a control, but we are not focused on the controller. Here we think K is a kind of controller, right? We choose different K, the system will have different behavior. Now we consider input is a controller. Input signal, you control the waveform of the input so that the output satisfy certain requirement. Yeah, we can also have that kind of things. Yeah. But for detail, you need a little more. You can read that textbook. I listed it as a reference. You can also have some other courses like 550. Yeah, in 550, it will give you more details. Yeah. All right. Okay, what's the time? I only used 28 minutes. So all the material, the new material, no more new materials. So that means we finish all the material we have, all the knowledge we want to study in this course. And then the next step will be a review. So I gave a review right now or next time? Next time. Okay, so this is a video. I just stop here. In this video I stop here. Then I record another video for the review. Okay. Yeah. Okay, see you in next lecture, next video. Bye bye.